Solving exponential equations. So we have a property of equality for these exponential equations that will be key to solving these. So here's the algebra speak. If b is a positive real number other than 1, and b to the x is equal to b to the y, if and only if x and y are also equal. So here's what this means in actual everyday English. So basically, if we have 3 to the x equals 3 to the 5th, because their bases are the same, then that means that x is equal to 5. When the bases are the same, you can set the exponents equal to each other. And you also have, well, if I go the other way, if I know that x is equal to 5, then I can raise these both to the same base, like 3 to the x and 3 to the 5th. I could also do 4 to the x and 4 to the 5th, 6 to the x, 6 to the 5th. As long as the bases are the same, the exponents are equal. So here's the general steps for solving equations with the same base, or something that you can make into the same base. Rewrite the problem using the same base for both sides of the equal sign. So like if we look at example 1, 2 raised to the x plus 6 equals 2 to the 5th. So in this case, the bases are both the same. So I don't even have to worry about step 1 because the bases are already the same. They're both 2's. Then use the property of exponents to simplify if necessary. Well, I can't do anything with pluses in the exponent, and I can't do anything with just a plain old 5. Step 3, drop the bases and set the exponents equal to each other. So that's the first thing I can do. So since the bases are the same, I don't need them. That means I can take this exponent, x plus 6, and set it equal to the other exponent of a 5. This I can solve very quickly. Subtract 6 from both sides of the equal sign. So x equals to -1. And there's my solution. 4. Solve 4 to the 2x plus 3 equals 1 over 32 to the 3x plus 1. So the two numbers I'm working with, 4 and, well, 32, I know those are both powers of 2. 4 is the easy one. I know that 4 is equal to 2 squared. That's the easy one. 32, I know is 2 to the 5th. But I don't just have 32, I have 1 over 32. Well, that means I need to make this 5 a negative. Since it's a fraction, that's what negative exponents do. They knock that base down to the bottom of a fraction. So let's go ahead and start replacing. 4 gets replaced with 2 squared, but then I still have this 2x plus 3 exponent on the 4 equals 1 over 32 gets replaced with 2 to the -5. There we go. But I still have this exponent of 3x plus 1 on that 1 over 32. Now let's use our property of exponents and multiply the exponents together since they're raised to each other. So 2 and then 2 times 2x plus 3, all in the exponent, equals 2 to the -5 times 3x plus 1, all in the exponent. So let's clean this up. So 2 times 2x, we have 2 to the 4x plus 6 equals 2 to the, distribute out the -5, -15x minus 5. Okay, now bases are the same, exponents are cleaned up. That means I can drop these bases and set the exponents equal to each other. Solve this for x. So add 15x to both sides, get your variables on one side of the equation. Get 19x plus 6 equals -5. Subtract that constant, so -6 from both sides. 19x equals -11. Divide by 19. X is equal to -11 over 19. Example 3. Solve 9 to the 2x minus 5 equals 27. Okay, well, 9 and 27, I know those are both powers of 3. So for example, 9, I know that I can make 9 into 3 squared. So what I'm having now is 3 squared to the 2x minus 5 power, because the 3 squared takes place of the 9, but I still have the 2x minus 5 and the exponent. Now I also know that 27 is 3 to the 3rd. But since 27 is just a single number, I don't need parentheses or anything. I can just replace it as being 3 to the 3rd. So now I have the bases are the same. They're both 3's. Now I'm going to use that property of exponents again. A to the m to the nth power means multiply your exponents to kind of clean up my exponents a little bit. So this is going to be 2 times 2x minus 5 equals 3 to the third. And now distribute in your outside 2. 3 to the 4x minus 10 equals 3 to the third. Now that your exponents are cleaned up and the bases are the same, we can drop our bases and set our exponents equal to each other. Solve for x. Add 10 to both sides. 4x equals 13. Divide by 4. And x is equal to 13 over 4. Fractions are okay. So that was solving exponential equations with the same bases. Well, what happens if I can't make the base the same? So for example, if we look at 5, we have a base of 5 and a base of 18. There's no number that I can raise 5 to get me anything with raising 18. It's not going to happen. So we have another way to deal with this. And this also does work even if you can make the bases the same. So if you get stuck, this always works. So when you don't have the same bases, you're going to take the common logarithm or the natural log of both sides. Now, the only time you use the natural log is if you have e as one of the bases. It's the only time you're going to use that natural log. Anything else, we're just going to use a common logarithm which has a base of 10. So let's look at example 5, one step at a time. So 5 to the 2x minus 3 equals 18. Since I cannot make these be the same base, I'm going to take the log of both sides. So log of 5 to the 2x minus 3 equals log of 18. That's step 1. Step 2 is I'm going to use the property of logarithms, that power rule that we had. So that said, if it was log of x to the m, I could take that exponent and put it down in the front and make it m times the log of x. So I'm going to use that here. I'm going to pull this down to the front and I'm going to keep it in parentheses since it's more than one thing. Now I have log of 5 equals log of 18. Okay, now remember, it's x we want. So log base 10 of 5, this is just a plain old number. I know it looks funny, but it is just a number. So this is multiplying, so I want to get rid of it. So I'm going to divide out the log. That's the next step. So now all we have is 2x minus 3 equals log of 18 over log of 5. Now this right-hand side, there's no variables on that right-hand side. So this gigantic fraction thing right here, this is just a number. So use a calculating tool to approximate this decimal. Approximate with calculator of some kind. I'll put a link on your Google Classroom. So approximate this decimal, log of 18 over log of 5, and you're going to get 1.796. Make sure you round properly. Give me about 3 decimal places. Now I can finish solving this for x like a regular equation. Add 3 to both sides, so I get 2x equals 4.796, and divide by 2, I get x is equal to 2.398. And that's it. Let's try another one. Example 6. 8 to the 4x plus 1 equals 205. Okay, cannot get 8 and 205 into the same base, pretty sure anyway. So instead of sitting here for 5 hours trying to figure out what power of 8 will get me something that's similar to the power of 205, I'm just going to take the logarithm of both sides. So I'm going to take log of 8 4x plus 1 equals the log of 205. Okay, now I'm going to use my exponent property of logarithms to pull my variable, which is in the exponent, down. So in parentheses, 4x plus 1 times the log of 8 equals the log of 205. Now again, this is being multiplied, so to get rid of that log, I need to divide it out. So my log on the left make a 1 and cancels out. And we have log of 205 over log of 8. Now again, this crazy business right here is really just a decimal number. So use a calculator to approximate that decimal, and you get somewhere about 2.56. And then continue solving this for x like a normal equation. Subtract the 1, 4x equals 1.56. Divide by 4, x is equal to 0.39. Example 3. Solve e to the 4x minus 9 equals 56. Again, I can't make e into anything because e is that irrational number that never ends. So since it doesn't end, I'm not going to be able to get a whole number out of it, no matter what power I raise it to. So I need to take the log of both sides. But since I have a base of e, I don't want to take the common logarithm like I have been. I want to take the natural log, ln. E to the 4x minus 9 equals the natural log of 56. What you do to one side, you have to do to the other. Use your exponent property of logarithms to pull this 4x minus 9 down to the front. So again, in parentheses, 4x minus 9 times the natural log of e equals the natural log of 56. Now, here's where we're coming to something kind of cool. Natural log of e, well, if we remember, the natural log has a hidden base of e. So when your base and your argument are the same, that's the inverse. This is a 1. That can be said the same for log base 10 of 10. That's a 1. Log base 2 of 2. That's a 1. Log base 8 of 8. That's a 1. Anything that follows this pattern is equal to a 1. So instead of having to divide this out, just leave it alone. This is really 4x minus 9 times 1. That's really what that turns into. Equals natural log of 56. Well, 4x times minus 9 times a 1, well, that's just 4x minus 9. So natural log of e kind of went away all on its own. So I'm going to show you two different forms of this answer. Instead of finding a decimal approximation for this, I'm just going to leave it alone. Here's what we're going to do. We're going to keep solving. Plus 9 to both sides. So 4x equals, so natural log of 56 is a number, but I just don't know what it is. So we're just going to leave natural log of 56 alone. Then we're going to do plus 9. Then we're going to divide by 4 to everything. And we have x equals the natural log of 56 plus 9, all divided by 4. So what we have here is this is what we call an exact solution. This is not a decimal approximation. This is the exact solution. This is like leaving 1/3 as 1/3 instead of approximating it as 0.33. Now, you could, it doesn't matter, it just depends on how your answer choices are written, you could get the decimal approximation by substituting natural log of 56 into a calculator, and you're going to get something around the lines of 3.256. This is the approximate answer. These are the same thing. So if you have natural logs in your answer choices, or logs in general, you have an exact solution. If you have decimals, you have an approximated solution. Either of these are both correct answers. Solving logarithmic equations. So similar to solving exponential equations, logarithms are kind of around the same way. Since these are inverses of each other, they work pretty close together. So here's the algebra speak for this property of equality that we're going to need. So if b, x, and y are positive real numbers and b is not equal to 1, then that means log base b of x is equal to log base b of y if and only if x and y are equal. So here's an example. Let's think of what this actually says. So if log base 2 of x is equal to log base 2 of 7, then that means that the log's arguments, the stuff inside that logarithm, are also equal to each other. X equals 7. And I can go backwards as well. If x is equal to 7, then I can make x the argument of a log with a certain base equal to 7, the argument of a log with the same base. There's also this inverse property that we need to know. If I have an exponent and the base is b and its exponent is log with that same base, then, well, what happens is the base and the log kind of cancel out, and all you're left with is what the argument is. Whatever's inside, that's all you're left with. So let's solve some of these. So step 1, rewrite the problem using only one log on both sides of the equal sign. So number 1, solve the natural log of 4x minus 7 equal to the natural log of x plus 5. So both sides have one log. Step 1's good to go. Step 2, rewrite the problems without any logarithms. So there's two choices here. If you have 2 logs total, then that means you're going to use the equality property above. If you have 1 log and only 1 log, change it to exponential form. So for this example 1, we have situation A where we have 2 logs, one on both sides. So now they're both natural logs. That means their bases are both an e. So since it's a log with the same base on the left and the right, that means I can take their arguments and set them equal to each other. 4x minus 7 equals x plus 5. I can drop the logarithm portion. And then we're just going to continue to solve this like a regular equation. So I'm going to subtract x from both sides. So I get 3x minus 7 equals 5. Add 7, 3x equals 12, and divide by 3, x is equal to 4. Now, with logarithms, you have to check and make sure that you don't have a negative inside of a log. So before you stop and say, boom, there's your solution, you're going to have to go back and check. So we're going to substitute in 4 where x is. So 4 times 4 minus 7 equals natural log of 4 plus 5, and make sure I don't have any negatives inside the logarithms. So on the left, 4 times 4 makes 16, and 16 minus 7 makes 9, so that's a positive number, so that's good. And then on the right, 4 plus 5 also makes 9, that one's positive as well. So since both arguments are positive, that means yes, x equals 4 is in fact the solution. You always have to check because you cannot take logs of negative numbers. The x's have to be greater than or equal to 0. Example 2. Log base 2 of 5x minus 17 equals 3. So step 1 above says make sure that there's only one log on either side. So in this case, I only have one log, so step 1's good to go. Step 2 is rewrite the problem without any logs. So in this case, I have that situation B. I only have one log in this equation. So that means I'm going to have to change this into exponential form. So the way we do that is start with the base, raise it to the number across from the equal sign. So 2 to the third is equal to, and then the argument, whatever's inside the logarithm. So 2 to the third is equal to 5x plus 17. Now that we've written this without a log, we're just going to continue solving. So 2 to the third is equal to 8. 5x minus 17. Add the 17 to both sides, so we end up with 25 equals 5x. Divide both sides by 5, and we end up with x is equal to 5. But again, before we can say that yes, this is my final solution, I need to make sure I always go back and check and make sure I don't end up with a negative inside the logarithm. So log base 2 of 5, x is now 5, minus 17. So 5 times 5 makes 25. 25 minus 17 makes an 8. So log base 2 of 8 equals 3. The 8 is what is the problem. So since 8 is positive, we are good. And that does mean x equals 5 is the solution. Example 3. Natural log of 4x minus 1 equals 3. So step 1, rewrite the problem only with one log. That's not a problem in this case because I only have one natural log. Step 2, write the problem without any logs. So again, I have that letter B situation. I only have a single log to work with, so I need to change this into this exponential form. So we have to remember that natural logs have that hidden base of e. So we're going to take that base of e to the third, so e to the third equals the argument, 4x minus 1. And now we're going to continue solving. I'm going to go ahead and use my calculator to get a decimal approximation for e to the third. So I have about 20.086. Then I'm going to continue solving, add 1 to both sides, 21.086 equals 4x, and then divide by 4 on both sides. X is equal to 5.272. And again, we do need to check and make sure that this is not going to give me a negative number. So here's my check. Natural log of 4 times 5.272 minus 1. Well, 4 times 5.272, that's going to give me 21.086. Subtract 1, which is 20.086, which is definitely positive. So yes, 5.272 is my solution. Example 4. Solve log of 2x plus log of x minus 5 equals 2. So step 1 is I need to get a single log on either side. So I have 2 logs in this case. So I'm going to have to use my properties of logarithms to condense this down into a single log. So I see that these logs are being added. So that means I'm going to use the product property and multiply the 2x and the x minus 5 inside my logarithm. So these condense down into log of 2x times x minus 5 equals 2. Now before I mess with this any further, I'm going to go ahead and simplify this inside. So 2x times x makes 2x squared. 2x times negative 5 makes negative 10x, and then equals 2. So now I have to get rid of my logs, and I only have one log, so that means I'm going to have to use the exponential form. So log without bases really has a hidden base of 10. So 10 to the second power is equal to the argument, equal to 2x squared minus 10x. Well, I see that I have an x squared here, so I'm going to have to solve a quadratic equation. So 10 squared is 100. Then I need to move that 100 to the other side with everything else. So I have 0 equals 2x squared minus 10x minus 100. So I'm going to have to solve this by factoring or quadratic formula. Well, before I do either one of those, I see that all of these can be divided by 2, so I'm going to divide by 2 on the entire equation. 0 divided by 2 makes 0, 2x squared divided by 2 makes x squared, negative 10x divided by 2 makes negative 5x, negative 100 divided by 2 makes 50. So I'm going to have to do this by factoring. Well, since a is equal to 1, I can do my shortcut and just go ahead and set up my factors and find the two numbers. So I need numbers that multiply to a negative 50, but add up to be negative 5. Well, those two numbers are going to be negative 10 times a 5. Negative 10 times 5 makes negative 50, and if I do negative 10 plus 5, I get negative 5. Set each factor equal to 0, and then solve each factor for x. So I get 10 equals x, and on the other equation we have negative 5 equals x. Now remember, we can't assume that both of these are solutions. We have to make sure we check them and that we don't have any negatives inside of our logs. So I'm going to use the original equation. So I have log of 2x. I'm going to check the 10 first. So log of 2 times 10 plus log of 10 minus 5. Well, 2 times 10 makes 20. That's positive. Log of 10 minus 5 makes 5, which is also positive. So that means that x equals 10 is a good solution. Now let's check the other x. Log of 2 times x is negative 5 now, plus log of negative 5 minus 5. Well, 2 times negative 5, that's negative 10. There's already a negative inside of a log. That means that negative 5 cannot be a solution. So the only solution to this equation is x equals 10. Example 5. Solve log base 4 of 2x plus 1 equals log base 4 of x plus 2 minus log base 4 of 3. So step 1 is getting everything down into a single log on both sides. So my left-hand side of the equation is ready to go. There's only one log. That one is perfectly fine. On the right, however, I have 2 logs. So I need to use my properties of logarithms to condense this down into 1. So I see there's a minus in between. That means I'm going to have to use the quotient property and divide the arguments. So x plus 2 over 3 inside of a single log. Now that everything's condensed, step 2 is I'm going to have to get rid of the logs. Well, I have 2 logs on both sides, both with the same bases, so that means I can take their arguments and set them equal. So 2x plus 1 equal to x plus 2 over 3. So I'm going to solve this by using cross multiplication. So 2x plus 1 times 3 equals 1 times x plus 2. So let's simplify this down. 3 times 2x makes 6x. 3 times 1 makes 3. 1 times x makes x. 1 times 2 makes 2. Subtract x from both sides. 5x plus 3 equals 2. Subtract 3. 5x equals negative 1. And then divide by 5. So x is equal to negative 1/5. So remember, we need to check and make sure that this negative 1/5 is not going to make a negative inside any of my logs before we can say that this is the answer. So I'm going to check each log individually. So the first log was 2x plus 1. So 2 times negative 1/5 plus 1. Let's check that one. So this is going to be negative 2/5 plus 1, and negative 2/5 plus 1 makes 3/5, which is positive. So far, so good. The next log that had a variable in it was log base 4 of x plus 2. So x was negative 1/5 plus 2. Negative 1/5 plus 2 makes 9/5, which is also positive. So yes, x equals negative 1/5 is a solution.